We see our solar system as a safe haven in a violent galaxy, but distance is our only protection. Before encountering the mind-bending horrors of deep space, we must survive the monsters nearby, where rain is acid, air is metal, and even the least threatening places are deadly. Venus exemplifies this. Its surface pressure is 91 times Earth's at sea level, akin to being nearly a kilometer underwater. Its stable temperature is about 467 degrees Celsius, hot enough to melt lead. Sulfuric acid clouds, composed of 75 to 96% acid, envelop it. Soviet Venera probes, the only machines to land there, lasted around 2 hours before being destroyed, a duration matching the most durable hardware ever on another world. Jupiter's radiation belts extend roughly 300,000 kilometers from the cloud tops, with high-energy electrons moving at nearly light speed, producing synchrotron radiation. The Galileo spacecraft, orbiting from 1995 to 2003, suffered repeated electronic degradation despite heavy shielding. Future crewed missions near Jupiter would receive fatal radiation doses within hours. The Europa Clipper mission is designed to orbit elliptically, dipping in and out of the radiation zone. Io, Jupiter's innermost large moon, hosts over 400 active volcanoes. Tidal forces from Jupiter and nearby moons generate internal friction, keeping Io's interior molten. Its largest volcano, Lokipatera, a 200-kilometer-wide lava lake, periodically collapses in spreading waves. Material from eruptions extends into Jupiter's magnetosphere, increasing radiation across the Jovian system. These places are terrifying by any human standard, yet they are relatively calm compared to what lies beyond. In the solar system, matter remains intact. When a star significantly more massive than our Sun exhausts its fuel, it does not simply fade. It collapses, then explodes. The outer layers are blasted outward in a supernova. The core compresses until it crosses a threshold where ordinary matter cannot exist. What remains is a neutron star. A neutron star is the compressed remnant of a stellar core, typically packing more mass than the Sun into an object roughly the size of a city. Its density matches that of an atomic nucleus sustained across an object 20 kilometers wide. A single teaspoon of neutron star material would weigh billions of tons on Earth. The surface gravity is so intense that the escape velocity approaches a significant fraction of the speed of light. Many neutron stars rotate rapidly and emit beams of radiation from their magnetic poles. These are pulsars. Some rotate hundreds of times per second, millisecond pulsars, maintaining this rhythm with the stability of an atomic clock. If you were in the path of a pulsar beam, you would be exposed to a natural particle accelerator firing high-energy radiation at you with metronomic regularity. The Sun's own future belongs to this level, even though it lies 5 billion years away. As the Sun exhausts its hydrogen, it will swell into a red giant, potentially expanding to or beyond Earth's orbit. Mercury and Venus will be consumed. Earth's oceans will likely be evaporated long before this. Increased solar luminosity in roughly 1 billion years will trigger a runaway greenhouse effect that ends complex surface life. After the red giant phase, the Sun will shed its outer layers, leaving behind a white dwarf, an Earth-sized remnant that slowly cools over billions of years, eventually becoming a cold, dark object that no longer radiates energy. Some planets may survive in altered orbits, others will be consumed or scattered. The solar system ends not with an explosion, but with a long, slow cooling into darkness. Magnetars are a subclass of neutron star, and they represent a qualitative escalation in how dangerous a single object can be. Their magnetic fields are approximately 1 trillion times stronger than Earth's. At distances of around 1,000 kilometers from a magnetar, those fields would in principle be strong enough to distort the electron clouds around atoms, tearing matter apart at the quantum level before any conventional hazard could act on it. Magnetars occasionally release energy in what are called starquakes. These are failures in the star's crystalline crust, driven by the enormous magnetic stress built up within it. A single starquake releases more energy in fractions of a second than the Sun emits over thousands of years. On December 27, 2004, a magnetar designated SGR 1806 released a giant gamma-ray flare from approximately 50,000 light-years away. This flare was energetic enough to measurably disturb Earth's ionosphere, the upper layer of the atmosphere, for several seconds. Analyses suggest that if a comparable event occurred within about 10 light-years of Earth, the radiation dose delivered to a planet's surface could be extinction level. In April 2020, a magnetar within the Milky Way produced a radio pulse consistent with the class of signals known as fast radio bursts. high-intensity millisecond pulses typically detected from cosmological distances. This was the first time an FRB-like signal had been confirmed from within our own galaxy, demonstrating that the compact objects behind some of these events are active and local. What makes magnetars particularly unsettling is that they are, in visible light, largely unremarkable. A magnetar sitting within a few dozen light-years of Earth would not be easily flagged as dangerous by casual observation. The hazard is invisible until it erupts. Gamma-ray bursts are the most energetic electromagnetic events observed. For a few seconds to a few minutes, a single gamma-ray burst can briefly outshine an entire galaxy in high-energy photons. They fall into two broad categories based on duration, both involving black hole formation. Long-duration gamma-ray bursts, lasting more than 2 seconds, are understood as collapsers. In this model, the core of a rapidly rotating massive star collapses directly into a black hole. Infalling material forms a dense accretion disk around the black hole, launching powerful relativistic jets that bore through the star's outer layers and extend into space. These jets travel near the speed of light. If one of these jets points toward Earth from within a few thousand light-years, it could deliver a gamma-ray bombardment capable of stripping the ozone layer from a planet's atmosphere. Without ozone, the surface would be exposed to intense ultraviolet radiation. The bombardment lasts seconds to minutes, arriving without warning from a star that might have appeared normal in visible light only hours earlier. Short-duration gamma-ray bursts result from neutron-star mergers. When two neutron stars in a tight binary orbit collide, the explosion emits gamma rays and gravitational waves and synthesizes heavy elements like gold, platinum, and uranium, scattering them into space. The 2017 detection of GW170817, a gravitational wave signal paired with a short gamma-ray burst, confirmed this mechanism. Some gamma-ray bursts may also be powered by a magnetar briefly existing after a collapse before becoming a black hole. In this scenario, the magnetar acts as a reservoir of rotational and magnetic energy, releasing it suddenly in a catastrophic burst when it can no longer hold together against gravity. This links magnetar flares, short gamma-ray bursts, and fast radio bursts into a single evolutionary chain. A black hole is a region of space-time where the curvature of space becomes so extreme that nothing, not matter, not light, can escape once it crosses the boundary called the event horizon. This is not a metaphor. It is a geometric property of space-time itself, a consequence of general relativity that has been confirmed through multiple independent observations. When gas falls toward a stellar mass black hole, it does not fall straight in. Conservation of angular momentum causes it to spiral inward, forming an accretion disk. Friction within the disk heats the gas to tens of millions of degrees, producing intense X-ray emission. This is how X-ray binary systems work. A black hole consuming a companion star, its accretion disk glowing brightly in wavelengths invisible to the human eye. Near the event horizon, general relativity predicts several effects with no analog in everyday experience. Gravitational redshift stretches light to longer wavelengths as it climbs out of the gravitational well. Frame dragging means that a rotating black hole actually drags space-time itself around with it, so that any object near it is swept along whether it wants to be or not. The innermost stable circular orbit marks the last point at which matter can orbit without inevitably spiraling inward. Beyond it, the plunge is irreversible. Supermassive black holes at the centers of galaxies extend this influence to cosmological scales. Their jets and outflows carve cavities in the hot gas-filling galaxy clusters, voids tens of thousands of light-years across, visible in X-ray observations as ghostly absences. These cavities act as thermostats for the cluster, regulating how much gas can cool and form stars across regions containing hundreds or thousands of galaxies. A single black hole can thus control the thermal history of an enormous volume of the universe. The information paradox remains unresolved. Physics says information cannot be destroyed, but anything crossing the event horizon appears to be lost to the outside universe. Whether information is preserved, scrambled, or truly erased at the event horizon is one of the deepest open questions in theoretical physics. A blazar is a specific type of active galaxy in which the supermassive black hole at the center has launched a relativistic jet aimed almost directly at Earth. This distinction, the orientation of the jet, is what separates blazars from other active galactic nuclei and makes them a distinct category of cosmic hazard. The jets extend for thousands to millions of light years. Within them, particles are accelerated to energies that dwarf anything achievable in terrestrial accelerators. These jets produce emission across the entire electromagnetic spectrum, from radio waves to the highest energy gamma rays ever detected. Blazars are the dominant contributors to the extragalactic gamma-ray background, the diffuse high-energy light that permeates the universe. Despite being only a few thousand known objects, the emission processes within blazar jets are not fully understood. Theoretical models disagree about whether the gamma-ray emission originates close to the black hole, far out along the jet, or in multiple regions simultaneously. The jets also show rapid variability. Their brightness can change dramatically over hours, which implies that the emitting regions are extremely compact, a constraint that is difficult to reconcile with the energies involved. Some models suggest that blazars represent a youthful phase of galaxy evolution, a period when the central black hole is accreting rapidly and the jets are at their most energetic. If this is correct, many galaxies, including our own, may have passed through a blazar phase in their histories. The Milky Way's central black hole, Sagittarius A star, is currently quiet. In the past, it may not have been. Looking at a blazar is, in a literal physical sense, looking directly into the aperture of a particle accelerator that spans a significant fraction of a galaxy. In the first microsecond after the Big Bang, the universe was hot enough that protons and neutrons did not yet exist. The matter filling all of space was a quark-gluon plasma, a state where quarks and gluons, the fundamental constituents of nuclear matter, moved freely rather than being confined inside particles. This was the universe's original condition, and one of the most extreme states of matter ever studied. Collider experiments at Brookhaven National Laboratory's relativistic heavy ion collider and CERN's Large Hadron Collider have recreated tiny droplets of quark-gluon plasma by accelerating heavy atomic nuclei to near light speed and colliding them. The temperatures briefly exceed 1 trillion degrees Celsius, hotter than the cores of any star today. The results overturned early expectations. Physicists predicted that quark-gluon plasma would behave like a gas, with particles moving relatively freely. Instead, measurements showed it behaves like an almost perfect liquid, with the lowest viscosity ever measured for any substance. It flows smoothly, and the collision geometry, whether two nuclei collide head-on or at an angle, produces different shapes in the plasma: elliptic blobs, triangular blobs, each bearing the imprint of the initial collision geometry. Recent experiments found that fast-moving quarks create wakes, pressure waves dragged behind them through the liquid, similar to a ship's bow wave. This confirms that the earliest matter in the universe was not chaotic fog, but a structured, dynamic fluid with weather-like behavior at scales smaller than an atomic nucleus. The implication is profound. The large-scale structure of today's universe, the cosmic web of galaxy filaments and voids spanning hundreds of millions of light-years, may carry fossil signatures of microscopic fluid dynamics from a trillion-degree liquid that existed for only fractions of a microsecond. The universe's largest structures were shaped in part by turbulence in a liquid smaller than a proton. The highest level of cosmic terror is not the most energetic or destructive. It is phenomena that remain fundamentally unexplained, objects and events documented by observation, reproducible in data, yet resistant to any complete theoretical framework. These are not mysteries in the colloquial sense of "we haven't figured it out yet." They are cases where current physics, applied rigorously, produces results conflicting with observations. Fast radio bursts with 16-day cycles emit pulses for roughly 4 days, then go silent for 12, repeating. The periodicity suggests some kind of orbital or precessional clock, but no standard Magnetar model produces this behavior. The source mechanism for the broader FRB population remains contested. Tabby's star shows irregular dimming of up to 22%, too deep, irregular, and prolonged to be explained by a transiting planet. The leading explanation involves circumstellar dust, but no model fully reproduces the light curve. Initially, researchers briefly considered artificial structure. The zombie white dwarf RxJ 0528 plus 2838, about 730 light-years away, consumes a companion star and drives a bow shock spanning 4,000 astronomical units, yet shows no visible accretion disk. Standard models predict one, but it is absent. Researchers call the power mechanism a mystery engine. Something channels and ejects material, likely a very strong magnetic field, but in an unexplainable configuration. The coronal heating problem, that the sun's outer atmosphere is millions of degrees hotter than its surface, remains unresolved after decades. Leading hypotheses involve Alfvén waves and nanoflares, but no single mechanism is confirmed as dominant. These phenomena share a disconcerting feature. They are close, observable, studied with the best instruments, yet fundamentally not understood. The universe is not withholding secrets from neglect. Some mechanisms are simply beyond our current explanation, making our model of reality incomplete in measurable, documented ways. The most terrifying place is the boundary of what physics can describe, not because something dangerous dwells there, but because we do not yet know what does. If these questions stay with you, there's more to explore. The universe keeps producing phenomena that rewrite our assumptions. Subscribe to keep going deeper, and check out this video next. Thanks for watching.